Hello everyone, I welcome all of you to the today's webinar on synergy between MIDAS Civil and MIDAS FE NX. My name is Saurabh Thak and I am Technical Support Engineer at MIDAS R&D Center, India. The purpose of this webinar is to showcase the effectiveness of MIDAS Civil and MIDAS FE NX in terms of interoperability. Before moving forward, let's discuss the contents of the presentation. In today's webinar, first we'll discuss various features and applications of MIDAS Civil and MIDAS FE NX pertaining to the modeling and design of steel bridges. Then we'll consider an example of steel arch bridge and we'll cover everything from the modeling to the design. In the later part of the webinar, we'll consider a steel joint in FEA NX and model it using the tools available in FEA NX and will perform the detailed joint analysis. Let's briefly discuss the features offered by MIDAS Civil first. Before discussing the features of MIDAS Civil, one should know that the MIDAS Civil is developed to keep in mind the modeling and analysis requirements of the general bridge structures. The features of MIDAS Civil are classified in three parts, that is modeling, analysis and design part. MIDAS Civil offers modeling through frame, plate and solid elements using node and element based modeling tools. It allows us to do the meshing of frame elements and plate elements with some limitations. Further, we have CAD based tools such as translate, divide, merge to generate complex geometry with ease for bridge structures. Further, we have extrude tool that enables us to create node to line, line to plane and plane to solid element, which is again very useful for creating irregular geometry. Further, MIDAS Civil offers elastic and plastic materials that can be used with time dependent material properties to consider the effect of time delay and construction sequence in the analysis. Further, MIDAS Civil offers a comprehensive library of sections which includes PSC sections, SRC sections, steel section, built-up section, composite section and user-defined section. These sections also include the standard sections available as per the international codes. Further, the USP of MIDAS Civil is Bridge Wizards of MIDAS Civil. It provides wizards for complex bridges. We have wizards for composite bridges, FCM bridge, which is based on the construction sequence of the bridge. We have wizard for suspension bridge. We have wizard for cable stay bridge, and several other wizards are available for generating a quick model for complex bridge structures, hence saving a lot of the engineer's time. Moving on to the analysis part of the MIDAS Civil. MIDAS Civil offers construction stage analysis, which helps in simulating the construction sequence, hence taking into account the effect of the time delay and the effect of different construction sequence. MIDAS Civil also offers moving load analysis, which simulates the movement of traffic vehicle and rail load onto the bridges. Further, for slender geometries, we have modal and buckling analysis for simulating the seismic events and the dynamic effect of the pedestrian and vehicular load. We have the response spectrum and the dynamic analysis in MIDAS Civil. For slender geometries, we can perform the nonlinear geometric analysis and nonlinear material analysis. Further, for mass concrete structures, MIDAS Civil offers heat of hydration analysis. In order to perform pushover analysis for the bridge structure, MIDAS Civil has a dedicated tab for it, which helps us identify the plastic hinge location, the yield status of the plastic hinge, and the performance point as per ATC 40 and FEMA. The another main core strength of MIDAS Civil is the design feature of MIDAS Civil. It offers design for steel and steel composite bridges and gives a comprehensive report that can directly be used by engineers for the submissions. Further, we have RC design, which allows us to design beam column, 1D plate and shell using sandwich theory, which is very useful for RC structures. Further, we have PSC design tool in MIDAS Civil that uh, generate a comprehensive design report for the PSC sections, and which is very time saving for an engineer. Further, MIDAS Civil allows bridge rating design for steel bridges and for concrete PSC bridges as per ASTO and CS 454 code. This tool can be used for the assessment and restoration of the existing bridges. These are the general features of MIDAS Civil. Now let's look at the post-processing tools of MIDAS Civil. The MIDAS Civil helps us to visualize the forces, deformation, and the entire structure. Further, the critical position of vehicle can be obtained for governing load case using the moving load tracer tool of MIDAS Civil. Further, we have options of generating camber tree for the manufactured or prefabricated precast structures and construction camber for cast in situ structure, which is very useful for precast for steel as well as concrete structures. Further, we have auto load combination generation tool as per the international codes, so that it saves a lot of time of manually creating the combination. Further, MIDAS Civil generates the design reports and the results in Excel compatible format, so that they can easily be copied to the Excel files where the calculations are being done. Further, in MIDAS Civil, we have dynamic report generator tool, which generates dynamic report in Word format that can be linked with the model file. So as soon as some data is updated in the model, that particular data gets automatically updated in that Word file as well. Hence the name is dynamic. Further, now we have gone through the capabilities of MIDAS Civil. We'll be using a few of these features in today's demonstration part of the webinar. Let's briefly discuss the capabilities of MIDAS FEA NX as well. MIDAS FEA NX is special purpose software created by keeping in mind the requirements for finite element modeling of irregular geometries used in civil and structure engineering applications. The features of FEA NX are divided into two parts. One is modeling part, another is analysis part. FEA NX supports object-oriented based modeling, where the geometry is created first, then the geometry is meshed to generate the nodes and elements. It offers specialized features such as extrude, sweep, revolve, fillet, chamfer, etc. for the generation of complex surface and solid geometries. Further, it offers Boolean operators which can fuse, cut, embed, intersect the two solids or surfaces, which is quite useful for creating complex geometries for the FEM modeling. In material properties, MIDAS FEA NX supports additional nonlinear properties over and above MIDAS Civil, such as smeared crack model, several other nonlinear soil models for generating the FEM models. Moreover, it supports nonlinear interface modeling for the simulation of bond slip, steel concrete interface, bolted connection interface, etc. Also, the amendment of rebar and tendons in plates and solids can be achieved, which is useful for the modeling of blisters as an example. Further, FEA NX supports construction stage analysis, buckling, response spectrum, dynamic interface analysis, cracking analysis for concrete structures, fatigue analysis for steel connections, etc. Let's look at few of the features explained. We'll be using them during the demonstration part of the webinar. Advanced meshing tool of FEA NX allows the mesh control along the different edges from fine to coarse. As you can see in this particular image, the meshes is being varied from fine at the center to the coarse as we move away from the center of the pier. Further, for a diaphragm section, the fine to coarse meshing is being done in order to get better results from the analysis. Further, we have Boolean operators in FEA NX, which helps us to combine two particular objects, solid objects. So we can fuse these objects. We can make a impression or make a cut through the intersection of these objects. Further, we can embed one particular object in another object, which is useful for embedding tendons and embedding rebars in a solid or a mass concrete. Further, we have CAD-based tools such as revolve and sweep, where we can revolve a linear element along a particular axis, or we can sweep a particular linear element along a guide curve to create complex surface and solid geometries. Further, we have options of trimming the surface, where we can trim all the all the pipes connecting at a particular node in order to create a properly jointed surface, as you can see in this particular image. Further, we have loft command to taper the geometry from one section to another section, as you can see in this particular image. Let's look at the post processing results of FEA NX. The MIDAS FEA NX gives uniform contours for stresses, deformations throughout the solid. The clipping tool can be used to check the stresses inside the solid at a given section. As you can see in the image over here, where a section is being cut at the center of this particular connection, so that we can see the stresses at the internal location of this particular joint. Further, we have probe tool in MIDAS Civil, where we can extract the result at a given node of the solid. As you can see in this image, the probe tool, when we click at this location, we can get the stresses at this particular location. Further, we have advanced analysis tools such as fatigue analysis to determine the damage and life cycle of a particular jointed connection as per the codal provisions. Here are a few of the examples where civil and FEA NX were used in tandem. This is an example of a footbridge where the bridge is modeled using frame elements, and here you can see several members are connecting at this particular node. The global model created in civil will allow us to design individual members, but the local stresses generated at the joints cannot be determined from the civil model. Hence, it is necessary to design the joint using finite element modeling that will help in determining the local stresses at the joint location, so that steps can be taken to ensure stresses are within permissible limits. The joint is modeled using FEA NX in this particular case. Similarly, for orthotropic decks, there are cutouts and corrugation in the deck elements, which results in local stresses at those locations. Such applications require FEM-based modeling to determine local stress distribution, plate buckling, and plastic strain distribution. Further, for advanced applications such as fatigue analysis of connections to determine life cycle and damage, FEM-based modeling is required. All this can be achieved using MIDAS FEA NX. Let's move ahead with the example model of steel arch bridge to understand the interoperability of MIDAS Civil and MIDAS FEA NX. Till now, we have seen various features and applications of MIDAS Civil and MIDAS FEA NX. Now let's take the example of steel arch bridge to understand the entire process. These are the steps involved in modeling, analysis, and design of steel arch bridge. The global model of bridge using frame elements is created in MIDAS Civil first. Here, material, sections, loads, and boundary conditions are applied to the structure. Further, global, linear, and non-linear analysis and buckling analysis, if required, is performed for the structure in MIDAS Civil. Further, moving load analysis, response spectrum analysis, and other analysis are performed on the structure. The results of each analysis for each load case are saved at this particular stage. Now, the next part would be to design for the results obtained. So, the combinations are made as per the required codal provisions, and the design tool of MIDAS Civil is used to perform the strength and serviceability based checks for each and every members of the steel arch bridge. Further, the sections of the bridge can be optimized using optimization tool of MIDAS Civil for steel design. Once the member design is completed as per the global model, the next step is to model the joint of that particular model where several members are being connected. So the joint is taken from civil to FEA NX where the boundary conditions are given and the model is recreated and meshed for the further processing. Here the loads or displacements are applied at the given location. Now next step would be to perform local linear or local non-linear or local buckling analysis to get the required stress distribution, plastic strain or buckling strength for this particular joint. Further, advanced analysis such as fatigue analysis can also be performed if required for this particular joint. For the scope of this webinar, we'll be doing linear analysis of the joint generated from the MIDAS Civil model. Let me just discuss our structure. This is a steel arch bridge of span of 50 meters. The deck width is 14 meters and the maximum height of the arch is 10 meters. Now let's discuss the components of the bridge. So these are the components of our steel arch bridge. We have two main girders in blue color and a stranger beam at the center. The main girders are connected to each other with the cross beam as shown over here. At the bottom, we have bracings connecting these cross beams. Further, we have arch rib connecting the ends of the main girder. The arch rib and the main girder, they are connected with the help of vertical member and the diagonal members and the spank. Further, the two arch ribs are connected to each other with the help of strut members, and we have provided the bracings to support these strut members as you can see over here. Further, to this bridge a simply supported boundary condition is provided as you can see. So let's move on to the demonstration part of the webinar where we will model, analyze and design this entire structure. This is the GUI of MIDAS Civil, where all the options are arranged in very intuitive manner in the main menu. As you can see, this is the ribbon menu where all the options can be accessed easily by the user. Further, we have quick access toolbar for the selection options and the display option. Then we have another toolbar over here to change the view and select the dynamic view. So let's discuss each tab one by one. In the view option, the tools related to view can be accessed. In a structure tab, we can select the wizard that are to be used for a given structure. We have standard wizard available in MIDAS Civil that can be easily used for generating complex geometries. Then this is the node and element tab, where the tools related to creation of the nodes and creation of the line elements and the creation of the map or the meshing of the plane element that can be used. In property tabs, the material properties, time dependent material properties, plastic material properties, the section properties can be selected from this particular tab. In boundary tab, we can define the boundaries to be given to our structure. So it is the support condition that is to be provided to the structure. So today we'll be using the define support tool for defining the simply supported condition for our bridge. In load tab, we have static load, dynamic loads, settlement loads, temperature pre-stress loads, construction stage loads, load tables. Then we have moving load, heat of hydration. So these tools can be used for applying the loads onto our structure. We'll be using a few of them to apply the loads for today's structure. In the analysis tab, we can control the analysis option, select a particular type of analysis. These are the analysis available in MIDAS Civil. In results tab, we can check the results after the analysis and interpret them as per our requirement. In PSC tab, it's a design tool for PSC sections, and the PSC sections can be designed from over here. Pushover tab is dedicated to pushover analysis. Design tab includes the design of steel members, design of RC members, design of SRC sections, design of composite sections. So it includes the steel composite bridge design as well. In rating tab, this is used for the assessment of the existing bridges for the steel and PSC bridges. Here H2 and CS454 codes can be used for this particular purpose. So this is my base file, and we'll be creating our model in this file. In this particular file, I have already defined the material properties. So today I'll be using the steel material of S355 grade based on Eurocode 5. We can change the code if we want to, or change the material type from over here. We'll be assigning this material to all our members. Then I have already defined members that are to be used in our structure. So for main girders, a user defined section is selected, and I have defined a box section. For that, this is the various parameters. These parameters are being put based on the guide diagram shown over here. H is the depth of the section, B is the width of the section, TF and TW is the thickness of flange and thickness of web over here. Similarly, other sections were also defined. Now let's start with the modeling part.
We'll first start with creating a parabolic arch. So I'll go to structure. In base structure, I'll select arch. Here we have an option of creating arches by these methods. I'll select parabola 1 method. I select the number of segments as 10. Span length would be 50 meters and height would be 10 meters. I'll select material as S355 and section of arch would be arch rep. We'll insert it at a origin in XZ plane. Here I'll select none for the boundary condition. We'll create the boundary condition later. Let me press OK, and this is generated with the section properties. Now I'll project these nodes vertically to create the vertical members. So let me just select all these nodes. I'll remove the element number from over here so that only nodes are selected. Now in order to project it, we'll be using extrude command. So we'll be using extrude node to line element, and we'll be projecting this on the x-axis. So I've selected the section type as verticals because these are our vertical members that we'll be creating. We'll use project on between these and these two. So along this vector, normal to this vector, this will be projected. Once I click apply, these elements are created. Now let me create our main girder. So S355 main girder is selected. I'll check on the node intersect and element intersect. So everything between the lines path will be intersected, and hence this is intersected. We can check it from shrink view where the intersections are happening. Now I'll create the diagonals. We can create the diagonals manually, or we can do it for the half the structure and mirror it for the remaining structure. So I'll do that. I'll first select the section as diagonals and manually create for the half the structure. So for this here, this, I'll mirror that for about this plane. So the direction about YZ plane is to be taken. This is my point, which is 25 meter from the origin. Should intersect node and element, copy node attributes, copy element attribute, and reverse element local axis. We'll select the these diagonals elements manually. So there are different ways of selection. So I'm currently using manual way. So once I press apply, it's mirror about this particular plane. Now this one plane is ready. Now we'll translate this plane to create a 3D structure. So before moving forward, let's check our members. So these are created correctly, but our vertical member should be rotated such that our flanges should face normal to our truss plane. For that, we need to rotate the local axis about x-axis. So this is currently the the local axis direction. I'll use change parameter option. So in the node element, we have an option called change parameters. I'll select the verticals first based on the section type. So I'll go to this particular select elements by identifying. I'll identify the section of the material, which is the vertical section, and all these members are selected. Okay, now I'll change the element local axis or rotate the element local axis. We have an option called reverse element local axis that can also be used. Now the elements local axis is aligned from bottom to top, which is need to be consistent with the other members as well. Now we'll rotate it by giving it a beta angle. So we'll select the element local axis over here and give it a beta angle of 90 degree. We'll select select previous selection so that all the members which were previously selected will be selected. Once I give a beta angle, the element orientation has changed. Now the orientation of my vertical element is correct. So let's move on further with the modeling. I'll switch off the local axis from here. Now let's translate my structure. I'll select all the structure, translate it in direction of y by 14 meters. Okay, I'll use translate intersect element node, copy node attributes, element attributes. So I press OK. A 3D structure is created. Now I want to extrude my bottom nodes to create the cross beam. So I'll select my bottom nodes from here, go to this 3D view. So element and nodes are selected. I'll just delete the elements from here so that only nodes are selected. So bottom nodes are selected. Now I'll extrude it to create the cross beams. Go to extrude, select cross beam from over here, node to line extrusion, translate in -14 direction. It's translated. Now the cross beams are created. Similar fashion, we can extrude the top nodes as well, and the member for that would be the strut type. So let's do that. Extrude command, strut -14, apply. So the struts are created. Now let's divide these elements to create the stranger beam. So further, let me just divide these and let's see what happens. So I'll divide in two parts. These are the options for dividing. You can divide in an equal part. You can divide using other parameters as well. Currently I'll use the equal distance option. And so a node is created. Now I'll create the stranger beam. So I'll select bracing and stranger, node connectivity 41 and 42, and I will check node intersection and element intersection so that all the nodes and elements will be intersected in between. Now bracings need to be created for the top and bottom. Similar fashion, I'll select these as well and divide them, and I'll join it with the help of bracings. Divide elements, two parts. Select the bracing elements, bracing and stranger. Now using node connectivity, select this. I'll create the bracings for half part of the structure. For the remaining half, we'll be using mirror command. Now let me just translate these two first. So I'll translate along X 5 meters for 1, 2 and 3 span. I'll translate it for the next 4 spans, and for the remaining span I'll use the mirror command. Intersect node element, node attributes, select these two bracings, and apply. These are translated now. Now what we can do now, we have to mirror these about the planes. So what I'll do, I will select the bracing and stranger members. I'll go to section and select the bracing stringers over here. Okay, now I'll mirror it about this plane, vertical plane. So let's use the mirror command. So this is my vertical plane. Node intersect node elements, copy element attributes towards element local axis. Once I click apply, this is mirrored along with the bracings, and we have received a warning that a few of the elements are overlapping because we have created this stranger for the entire span of the structure. So we have a very simple option to check the duplicate members and easily delete those members. So in a structure tab, we have check duplicate elements. Once I click to check duplicate elements, it will automatically identify the duplicate elements and delete it. So 10 elements are deleted over here from 93. So the elements are mentioned over here. Now this is the elements, remaining elements, and it was found, creation was found over here. Now if we check the element number, we'll see there are no duplications anymore, and the software automatically checks that, so no need to worry about it. So our structure model is complete. Let's just give the boundary conditions to this model. So I'll go to the boundary tab now. Def Define support for this. So for this support, I would like to create it as fixed, in three translation direction, and this support would be free in the global y direction. This support would be free in global x and fixed in y. This would be free in x as well as y direction. Hence the support conditions are applied. Now next part would be to apply the loads on this particular model. Now to apply the loads, we'll go to the load tab, we'll select static loads, and we'll create load cases. We'll be defining very simple load cases. One is the dead load that will be applying onto our main girders, selected as dead. Then we'll apply sidewalk load that again will be applied onto the main girders as UDA. We are considering this for simplicity, so only these two cases are considered. I'll go to element, I'll select the load case as dead, I'll apply WS minus 90 kilonewton per meter, and I will select the main girder member. So from identifying option, we'll go to the select section, select type of section. Here we will select the main girders and click add. This will select this and will apply the loads on this section. Further, for the next load, that is again we'll apply the element load. Now I'll change from dead to sidewalk, and I'll apply a load of minus 6 kilonewton per meter on the main girder. So I'll again select the main girders from over here and apply a load of minus 6 kilonewton per meter as sidewalk load. So it's applied now. Let's check. So here we can check the loads applied. So loads are applied. Now we'll move on to the moving load, how to apply that. So in order to apply moving load, we need to first select the moving load type over here and define based on which code we want to apply the load. I'll select the Euro code, I'll select traffic line lanes. For simplicity, I'll consider a single lane at the center of the bridge. We can define these are the standard lane width, and we can change it if we want, and we can define the at an eccentricity, but for simplicity reason I'm applying it at the center of the bridge. Further, before doing that, let me first create a group so that we can apply the vehicular load onto the cross beam instead of the longitudinal beams. So in order to do that, I'll go to group, I'll select a structure group, I'll give it a name as cross beam. Now I'll identify the cross beam section from over here and assign the cross beams to it. Now this group is created with 22 elements. Again, I'll go to the moving load, traffic line lanes. I'll click on add lane. I'll go to lane 1. Lane 1, so this is the standard definition as per the Euro code. We can change the lane width, we can give the centricity to the lane, we can change the vehicle spacing. Further, the lane optimization tool in the transverse direction can also be used. We will not use currently for the simplicity reason. This is the vehicular load distribution. If you select lane element, the vehicle load will be transferred to the longitudinal elements. If you select the cross beam, the load will be transferred to the cross beam, and then from cross beam to the longitudinal beams. So we'll be selecting cross beam option. This is required for carriage kind of structure or structure with multiple beams. For a single line beam model, lane element is selected. Now we'll select the lane points at point 1 to point 2. This is the which lane will be provided, and once I click OK, this lane is defined as it is visible over here. Now I'll define the vehicle. I'll use standard LM1 vehicle. So LM1 vehicle is selected, and once I press OK, the standard definition is added. I'll create a moving load case by selecting the add option. I'll create LC1 LM1. Here I'll select the vehicle LM1 and no foot payload. I'll just add this particular lane, press OK, and this moving load case is created over here. So we can check that our sections elements, they are already assigned. We have defined the support condition, we have defined the loads, static loads, we have defined the moving loads, and moving loads are assigned. Now our structure is ready for the analysis. Let's run the analysis. So analysis is completed. We can check the results. So we'll go to results, and we can see the bending moment diagram and deformation for the structure. So this is the bending moment diagram for the structure for the various loads. You can select the loads over here, and for the moving load as well. So this is the moving load envelope for maximum LV max case. Further deformation contours and deformation displacement can be viewed from over here for the different load cases. Now we have a tool called moving load tracer that identifies the location of position of the vehicle for critical loads on any element. So suppose I want to check the position of the vehicle for critical load for the element number 97. I'll write the element number 97 over here, and I'll click apply. So this gives the position of moving load for this particular case. Without wasting much time on result interpretation, let's move on to the design of steel members. We'll go to design tab. Here we can select the code, and we have options to select the code over here also. So we'll select Eurocode 3 part 2, and these are the default options. We can change if you want for the different checks and what checks are to be performed and not to perform. Here we select the partial safety factor for the material. It is updated as per the code. No need to edit this as well. Then we can modify the steel material. Currently this is the original material. We can change the grade from over here. So we are not changing that. Let's close this option. Then we have to define the serviceability parameters for serviceability check. So we can just select all the members for the deflection control in beams and deflection control in column. These are usually not provided, but let's apply it to all the members. Apply, close. Now let's check the service load combination type. But before applying or giving this option, we need to define the load combination. So in the result tab, we first define the load combinations from over here. So we'll go to general. We have option to create auto load combinations, or we can create the combinations manually. So since we'll be using the combinations for the design of steel, we'll be doing it manually. So let's define LCB1. I'll be using very simple loads so that we can quickly see how the design is being performed. So these three load cases are added. I'll just make a copy of these three load cases as strength, and I'll make another for the serviceability. So serviceability part, I'll just create copy of these three. So these are the combination in the steel design tab we have defined. For that, checks are to be performed. Let me close this and again go to the design. So in the design, steel design, I will define my serviceability load combination. Here, whatever combinations we have defined, they are coming over here. So we will classify it to quasi-permanent, frequent, and characteristics. Based on that, checks will be performed. Say press OK. It's saved now. So this is the bending coefficient that is to be defined for the critical buckling MCR value. but we won't be defining. If it is not defined, it will take default value of 1 for the element. Again, no need to perform transfer stiffness, but we have an option to define transfer stiffness for these particular elements, so that the transfer stiffness checks can be performed for that. Now let's perform the steel coat check. So we'll just provide steel coat check over here. So now steel design has its design, and we have this particular tab where we can check the results. So once I select the members, or we can select the property of a member, and we can check the graphic report, graphic design report. So this is the report representing all the checks over here, the axial force that are being applied onto the member for the critical load combination, and for which the design is performed. So here you can see the axial resistance, the bending resistance check, the combined axial bending check, the resistance check, and the deflection check is performed for this particular section. Similarly, you can uh, check this for different properties over here, for property number 2, for property number 3, and this can also be checked based on the member number, so for in which member which is to be selected. Further, we can also check the detailed design report by clicking on to the detailed report. Here all the formulations and the codal formulas are mentioned, which can be further verified for manual calculation. So I'm closing this. Now we will see the optimization option, that is steel optimal design. So we'll click steel optimal design over here. Here we have option to select a particular member or all the members, so that structure or the software can itself optimize the design. So once I click the design and analysis tab, it will do some calculations, and it will update the member sizes to get the optimized section. So here these are the updated section. As you can see, previously this section was provided, now it has reduced the thickness of the section to 6 mm. So let's see what is the difference between the previous section and the new section. We have graph report, where the software reports what are the changes and what are updates being done. So this is, so old one was the red one, so this was the original weight of the structure, and green one is the new one, this is the updated weight. So it has reduced the weight considerably for each and every member, you can see over here. Further, this is the optimal weight, difference in the weight, and based on that the design is done. Then optimal design ratio. So previously ratio we have greater margin, now it has uh, gone close to the margin. So based on that we were able to optimize the section. So these are the result for the optimization. So we have done the design. Now let's move on to the modeling of joint. So let me close this, and we will see how to extract a particular joint detail from civil to FEA NX. I want to use this particular joint as several members are intersecting. Before taking it to FEA NX, we'll just divide these elements so that element length reduces. So the meshing would be in lesser element. So let me just use the divide command to divide this. I'll divide it in two parts, and I'll divide these longer elements in three parts. Now this joint detail I want to extract so that I can analyze the local stresses that are occurring at this, and I can further model it with the gusset plates that are going to come at this particular location. So let me just select this particular joint, and we have an option of exporting to frame section for solid. So this option can be used for generating the solid elements in FEA NX. So I'll just create this, select this object element. We can also use for generating or exporting the PSC section as well along with the tender profiles. I'll just use this, click OK. It's going to create a MCS file, that is the text file. I'll just give it a name, wish to save. So this is a text file where the details of and coordinates and the element type is selected, and this will be opened in FEA NX to export this particular detail, and further modifications will now be done in FEA NX. This is the starting window of FEA NX. Let me just enter the project title. "3D model gravity directions at units Newton meter in seconds." We'll press OK. This is the GUI. This is the main menu, which is created intuitively for the engineers to be used in the order of progression of the model. So since it's a object oriented model on the software, first we define the geometry, which may be point, curve, maybe surface, maybe solid. Then we mesh the geometry to create nodes and elements. Moreover, we have options to create elements in this, like the MIDAS civil. This main ribbon menu is fitted with lot many options so that user can easily identify these options and access those particular tools. So let's import our geometry from civil. In order to import our geometry, we have two options: frame to shell and frame to solid. Since we have converted our civil joint into solid, we'll use frame to solid option. We'll use select MIDAS section file, use arch bridge 2. Once I click OK, this geometry will be imported over here. As you can see, over here that there are several intersections that needs to be removed. So we have discussed tools to edit the geometry. We'll be using those tools to do that. First, we'll change the working plane. The working plane is currently set in this particular direction, that is the XY direction. We'll update it by going over here. We move the plane vertically so that we can easily create the gusset plates at the face of this particular members. First, we'll identify what is the width of the section so that accordingly we can shift the vertical plane. So from here to here we have a distance of 0.5. So let's shift the moving plane. We'll go to moving plane, move working plane option. We'll select a reference plane. So my reference plane would be this particular plane, and I will give it an offset of 0.25. So once I type 0.25 and press OK, this plane is created. Let's widen our grid. So currently width of the grid is 1 meter by 1 meter, which is okay for our usage. The number we can extend it as per our usage. So currently I am putting 50 value, hence the grid is extended. Now let's check the top view. So grid has formed at the face of this particular joint. Now we can create the gusset plate at this particular face and later copy it to the other face as well. So let's start then. Before creating the gusset plate, we need to edit these members. Since these members are intersecting, which is not acceptable, we'll be considering a plane over here to divide these elements. I'll use divide solid command to do that. I'll select the target solid and create a plane. So we have three options of dividing tool: select a tool surface, 3-point plane, and dividing plane. I'll be using the plane by giving it offset along the Z. So dividing plane by giving it an offset of 0.8 meters. We'll just take a look at a preview of this. As you can see, it's coming over here, hence everything will be divided from below over here. We'll just increase it to 0.9 so that intersection doesn't happen. Let's check out the preview. It's fine, and we'll press OK, and there is a check called delete original. So we'll press OK so that copy won't be created. So these are the elements which are divided. We can simply delete these elements but by selecting them and clicking delete. So this is our member, edited member. Now let's create the gusset plane. To create the gusset plane, we need to first define a few geometric points so that those can be used as references. So we'll be using point command. We'll select 3D point. We'll select a point on the surface. So this is my point, and the node is created over here. Now we have created a node at the center. Now I want to translate it. I'll select this particular tool, translate tool over here, and copy this node. Before that, I'll select it using the selection tool. So this node is highlighted, and here it is coming selected one target object. Now I'll copy it along a direction vector. I'll give a direction vector by selecting the center line of this particular object. So along this particular direction, the node will be created. And once I click over here, it is coming showing the distance between these 2 points I have selected. I want to create a node at the center of these two. I'll create by 2, make a copy and apply. Again, I want a node at the middle of that 2 as well. So the object is already selected. I'll just click 2.5 by 4 and click apply. The nodes are created over here. Similarly, I want to create the nodes at the other ends as well, so that a surface can be created. I'll give it minus 2.5, apply, then minus 2.5 by 2 and apply. Further, I want to translate these nodes to the top so that a gusset plate can be created. So let me just change my selection. So I'll unselect this particular node first and select my newly created node over here. So I'll go over here, and so this is the selection tool and this is the unselection tool. When I do this, I can unselect any particular node, and when I go over here, I can select any particular node. This you should remember while using this software. Also, let me select this as well. So we have two target objects, and I want to translate it up to over here. So I want to translate it. So I'll give translated at along this vertical vector. So let me just select the vector along this vertical direction. So I'll select the center of this. Let me just reselect from center of this to the center of this. So we have created this particular vector in the z direction 0.323, 0.33. Now I want to translate it by say, so each grid distance is 1 meter. So if I translate it by say 1.5 meters, it would be fine. So 1.5 meters, we'll see the preview of that. So it's coming over here. We can further translate it, or we can just click OK if we are satisfied with that. Let me just click OK. Now let's translate it along the x direction. So let me just select it again, use the translate command, because I want to create a gusset plate closer to the center element. So I'll use move this time. Direction vector would be along this direction. So I'll unselect this particular node and select just the first node. I'll move this by a distance of say 0.5. We'll see preview. That's fine. Now it's coming into the member. I'll move it by 0.3. Now this looks fine to me. Once I click apply, it will be moved. Let's translate the other node as well. Go to transfer command, translate command, select the target object, move it by a distance of minus 0.3, or it depends upon our direction vector. So I'll be moving from here to here along this direction vector. Once I click apply, we'll once see the preview of this. It looks fine. Let's see apply. So these nodes are created in this particular plane. Now I want to create a face, a gusset plate along this plane. So I'll use this particular profile command, polyline command, to do that. I'll click on this, 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 there, and there. So my line is created. Now I want to create a gusset along this particular edges. I'll just check off or hide the solids and click the make face option over here. I select the edges, name the geometry as gusset. We'll check the preview. It's okay. Once I press OK, the gusset is created. Now I activate the solid. It's looking like this, which is fine. Now I want to create a copy of this gusset plate at the other face. Since we know the width of our section is 0.5, I will just use the translate tool to copy this face. So this object is selected. Now I want to make a copy of this along a particular direction vector. So I'll give the direction vector from this point to the edge of that point. So this is the direction vector given. I'll click on this. So this is the minimum distance between these points, that is 0.5. So once I press preview, we'll see the gusset plate is generating. It looks okay to me. I'll click apply. The gusset plate is generated. Now since it's a plate and the other objects are solid objects, we need to convert it to solid for all the members to get fused. In order to do that, we'll select these plates and we'll extrude them. So I've selected this. I'll use extrude command and select extrude it to the solid. Again, I'll select the object, target object, then the 2-point vector over here. So from this edge to this edge, the extrusion distance should be the thickness of this particular plate. I'll give it a thickness of 0.02, that is a 20 mm plate. We can fuse it at this point as well. So I'll select the shape of this so that it gets fused with this particular joint. We'll preview it first before selecting it. So this looks fine. The plate is fused with this particular member. Once I click apply, this is generated. Further, we can do the same with the other object as well, other plate as well. So I'll select that plate. I'll give a direction vector. Now it will be in opposite direction from here to here. Again, the thickness of the plate would be 0.02, that is 20 mm. Extend fuse, base geometry would be our original one, so it will be fused. Preview would be this thing. Now once I press OK, the entire geometry is fused as well. Now the next part is to fuse all these members. So we'll do two at a time using the Boolean operators. We'll select this, we'll select these three members. Then we have an option called Boolean solid. Here we have fuse. So 4 objects are selected. and we will select the merge option, and once we press preview, this is the fuse geometry. So let's click apply. So this is fused. Further, we want to fuse this and this as well. Again, we'll select these two and click OK. Before that, we'll preview it. This looks fine. One more thing that I would like to point out, that there is a member which is protruding inside the member. So before fusing the geometry, we can divide it and delete it. We'll do it like that. Then we'll select the solid and check off the delete tool, and now we'll select the solid object, tool surface, and look at the preview and apply. So the member is divided. Now this member can be individually selected and deleted. Before moving forward, let's save this model. So this geometry, now we can fuse this geometry. We'll go to Boolean operator. We'll select fuse, select the target objects, and check on the merge faces, delete tool, and see preview. So this will be fused with that. Once I click OK, the entire geometry is fused as well. So the next part would be to mesh this particular geometry and again apply the loads over here for the analysis to happen. So we'll do it in a while. Let's do the meshing first. To mesh this geometry, we'll first go to the meshing tab. So we'll first define the material, go to isotropic and select a material from database. We'll select steel, then Eurocode 5, then S355 material. Press OK. Press OK. This material is saved over here. Now we'll divide this geometry by generate mesh tool. We'll select a 3D mesh and use auto solid option to mesh this. So this object will select this solid object. So this object is selected now. We'll select a mesh size of 0.1. Then we'll select the default tetra measure tool. Here property needs to be defined for the mesh. So we'll select the material to be isotropic and we'll press OK. This is given as 3D property. Now let's look at the preview. So seeds are getting generated at the edges. That means it is meshing properly and uniformly. Once we press OK, it meshes the entire geometry, as you can see over here. So the mesh is generated now. And now the next part is to create a central node for all these elements and connect it using rigid link. In order to do that, we'll be using geometry and create dummy nodes and dummy points over here, and then we'll assign nodes to it. For that, we'll create a diagonal connecting these two. So I'll select line 3D and connect the diagonal so that I can easily identify the central point of these diagonals. So before doing that, creating a node, I'll just create diagonals for all the members over here. So we have created the diagonals. This is the last one. So I'm not able to identify the node, so rather I'll check whether the node is available at the center. For that, I can create a center node between these two and create an intersection. So let me just do that. Create this line, create this line. Now create a connecting line from center of this to the center of this, as we can identify the midpoint of this. Now let's create points at the center of these particular lines. So from snap option we are getting this point, and we'll select 3D over here, then only we'll be able to draw the nodes. So sorry, the geometric points. So this point is created over here. Similarly, for all these sections, we'll snap this particular midpoint. Please note, snap point can be activated and deactivated from this tool. This tool can be used. So we have identified the center node for all this. So this is the geometric point. Now we'll create node at the geometric point. For that, we'll go to mesh. We'll go to node and create node. I'll quickly create nodes at these points, as I already know their positions. We can check the node numbers at a particular location in case we want to make sure that whether node is being generated over there or not. So generated, the node number is not present, so the node will create. Hence we have nodes created at all the intersections. Now let's define the rigid links for this particular structure. Now in order to create rigid link, we'll go to elements and create elements. We'll go others. Here we have option of point spring, rigid link, elastic links, and other tools. Here first we need to select a master node. After that we'll select the slave node. So we'll quickly select the master node. So master node is selected. Now we'll change our plane to select the slave nodes. So we'll use this polygon selection for the selection of slave nodes. So these nodes are selected. Please note this master node is also selected. So we'll go to pick select, unselect option, and unselect this. As we unselect this, this is the preview of this rigid link. Once we click apply, the rigid link will be generated. But for that, we need to first select the property, the rigid link. So we'll give rigid link over here. We'll select rigid body. We'll press OK. And once we press apply, the rigid link is created. In similar fashion, we'll create links at the other locations as well. So that's how rigid link can be created in this location. Now next part would be to apply the load or specified displacement at this location. We'll be applying specified displacement for a particular load case from MIDAS civil and apply it over here. Let's go to MIDAS civil to generate the specified displacement at these nodes. So these are the nodal points, and let me generate the results in tabular format. So we'll just select the points which are of our interest: 57, 59, 58. 63, 61, 64. So I'll copy these node numbers so that you can select them for displacement. So we'll be using LCB1. These are the displacement corresponding to LCB1 at these nodes. So point to be noted, these are the units are in mm. We'll copy these to FEA NX in mm. For that, we'll go to static analysis and define load. Okay. So we'll apply the displacement. So the name is displacement 1. We'll select the node one by one and apply the displacement coming from MIDAS civil. Before that, we need to ensure that the global axis in FEA NX and MIDAS civil is same. So for MIDAS civil, we have x along the span, y across the span, and with respect to the joint as well. If we go to FEA NX, we have x along the joint along the span and y perpendicular to the span. Hence, the orientation of global axis is same in both of them. First, we need to change the unit, that is in mm, and one by one we'll apply the displacement cases in this. So let's do that. Let's select node and apply the specified displacement. First, I'll apply the displacement at this node. I'll select this node. So one object is selected, and I'll go to civil and check the node number, which is the node number 57 for this. For corresponding 57, I'll copy the displacement. So it's 11.048. I'll copy it over here. Just fine. Then in y, we have 0.74 negative. In z, we have minus 0.53. Then in rx, we have this rotation. While copying, one needs to verify all the values are correct or not. So we can quickly copy that. Once we click apply, these specified displacement they are applied at this particular. In similar fashion, all the master nodes are to be applied with the specified displacement. The displacements are taken from MIDAS civil, and the same procedure is repeated for all the 6 nodes. As you can see, all the 6 nodes are loaded and we have 6 displacement cases over here. So next step is to perform the analysis. Let me just switch off the surface that we have used for the gusset extrusion. Okay, this looks fine. Now let's go to the analysis and perform the analysis. So as we will see what all tools are available, we'll give analysis name, joint analysis. So we have analysis control over here where we can control that initial temperature value and advanced geotechnical settings which I mentioned over here. Further, we can control output from over here. What are the outputs we want for this structure? We are keeping everything as default. This is the modules that we are going to run. So active set means whatever analysis case is to be created, whatever things are selected over there, that's going to be applied to the structure. So this is called module wise running analysis, or module wise creating the load case boundary condition. So we can activate any boundary condition and any load case by dragging it from here to here, and we can drag it back as well to remove that particular load or a boundary condition. We don't have to delete it from the model, just drag and drop from here or from here to here. So that's module wise application of load, boundary condition, and module wise definition of various analysis. So we'll press OK, and by clicking on this perform analysis button, the analysis can be performed. So it is selected this. One more thing I would like to point out, that we if we select solve each load set independently, then if we have applied 2-3 load cases, then they will be solved independently. But here in this case, okay, we have already defined our case, but here in this case only single load is applied, so no need to define that. Analysis is performing. See, analysis is completed now. We'll go to result tab and look at the various results provided by the software. First thing, we'll go to the results and see what are the results that are obtained for this. So these are the translation and displacement. Then we have total applied forces. Then we have reactions. Then we have solid stresses. We'll start with solid stresses. One message stress contour. So let's switch off the geometry so that we can have a better view. Okay, so these are the stress contours, one message contours. As we can see, this is the value of the stress in Newton per mm square, and we can see stress concentration is coming over here. We can check other results as well, but for this structure, it is the stresses that we are worried about, and we want to check that. Again, on double click on displacement, we will get the displacement contour. Okay, so suppose we are looking at the stresses. Now this is the stress contour. Now we have many options to get more detail about these stresses. If from here we can select the plane about which we want to clip this or we want to cut this. So say I want to cut this about y at 0 mm. So see, it will create a section over here, and we can check whether there are any stresses at the internal of this particular member. This will help us determine the stresses over here, and we can cater and design for that as well. Similarly, sections can be created at different locations. Let's look at another tool, that is ISO surface, where we can get the target value of stresses, and those values are highlighted over here, as you can see over here. Moreover, we have a tool called probe tool. From this we can further generate the results for this particular structure. So let's see how probe works. We'll click on probe. So we have this option. Here we can see at what node number we want our result. So we can just click it over here. We can get the result of stresses at this location, at this node. So we can generate the results at particular nodes around these structures. This is a very useful tool. We can get the stress results at a predefined node. So we can also type it here the node number to get the stresses or displacement or results at those particular location. This was about the result interpretations for FEA NX. So we have seen various result tools of FEA NX. Now let's see how can we export this geometry to MIDAS Civil so that it can become a part of the global model, and several such joints can be designed simultaneously for multiple load combination. For exporting the geometry, we'll go to the file menu. We have an option called export to MIDAS Civil file. So we'll select this option and we'll give it a name, joint new. We'll save it. Now I'll go to MIDAS Civil and I would like to bring my joint over here and do the analysis in this particular model. So for that, we first need to delete these members so that these members do not overlap with the geometry imported from FEA NX. So let's delete this. So the geometry is deleted now. Now, since we have defined a material number over there and a material properties over there, we'll be defining, updating this particular material number. We'll start it from 11 so that the materials coming from FEA NX do not overlap with this. Okay, so let's do that. Let's start with 11. Okay, and we'll assign this material to everything. So our material property starting on 11. Another point would be, before importing the model, that FEA NX model, we need to renumber our nodes and elements because the same numbers would be there for the geometry imported from FEA NX, and those numbers should not overlap, else geometry won't be exported. So we'll use this tool to renumber that. Before that, we'll see what is the last node number, last element number in FEA NX. For that, we'll try to export that file and check the node number in that that imported file from FEA NX. So this is the FEA NX file, and here we can see the node numbers. I'll check out the last node number first. So it is in the order of 8000. So I'll start to renumber my nodes in MIDAS Civil from 10,000. For the element number, I will check out the last element number, and here you can see it is going around 25,000. So I'll start the element number from 30,000. So I'll select all, check the node number, from renumber from 10,000. The start node number will be 10,000. Once I click apply, it's renumbered. Similarly, I'll rearrange the element and I will renumber it from 30,000 onwards. So the element numbers are renumbered. Now we will export the file from FEA NX. So that was the text file generated, which is compatible with MIDAS Civil. We'll delete this rebar data, as this might give warnings and error while exporting. So if we can just remove this rebar data because it is not required for this particular structure. And if we run it, our geometry should be exported here. We'll see. So we have zero warning, zero error, and the geometry has come over here. Now we can visualize our geometry. So it has come at exact that location, as you can see. Further, point to be noted that the rigid link point or the master node point will be overlapping in both the two cases. So we need to make sure that those nodes are getting merged over here. Once again, let's check the boundary condition for this model. As you can see, the rigid links are being imported from FEA NX as well. So that's a good thing for us. We don't have to define it over here. So I'll select this particular node and check there are two nodes over here. I'll use merge node command to merge these. Now if we check, we have only single node over here. As you can see over here. So these nodes need to be merged. See, there are two nodes. Again, I'll merge them. It's merged. We'll do similar exercise at all the edges. at all the rigid link master node of the rigid link. So nodes are merged now. Now we can perform the analysis for this compound geometry where we have the joint using solid elements and the other members are created using linear elements. The analysis is completed now without warnings. Let's switch off the boundary conditions and look at the results. So we'll go to result tab and we'll check the stresses in the solid. So for the dead load case, we are checking the von Mises stresses of ridge nodal result, legend, apply. So this is the stress contour we are getting over here. You can see. So this has become part of this particular steel arch bridge. Similarly, we can design other joints, or we can design a particular critical joint. Based on that, the plate thickness and the gusset plate thickness can be optimized. Let's move on to the presentation part.
To summarize, we have modeled a steel arch bridge, analyzed it and designed it in MIDAS Civil. After that, we took a joint where several members were coming. We exported that joint to FEA NX and remodeled it so that analysis can be performed, and we have checked the stresses at the interior and the maximum stress in the joint so that the gusset plates can be optimized based on the stresses obtained. So these are the results for a steel arch bridge. This is the axial force diagram at the top. Then we have our bending moment diagram for the steel truss bridge. This is from the global model, and we have this critical position for vehicular load at this location for this structure. Then this is the steel design optimization chart where the original quantity is compared with the updated quantity once the optimization design is done using the design tool of MIDAS Civil. So this is the geometry that we created in FEA NX and we exported it back to MIDAS Civil. As you can see, from local, so first we went to global to local to generate the proper geometry in solid using solid elements. After that, once we have got the results for the geometry created in FEA NX, we exported it back to our global model and wedged it at the required location so that it can become the part of the global model now. I hope this session might have given you a fair idea about the capabilities of MIDAS Civil and MIDAS FEA NX and how these two softwares can be effectively used to generate global to local model and again take back the local model to the global analysis. That's it from my side. Thank you.